so now let's go ahead and move on. Galaxies, here's what Hubble discovered. Galaxies have red-shifted light. Now, what does that mean? Doppler shift. Light will Doppler shift just like sound does. Remember sound? Meow. So they had trouble figuring this out for a while, and Hubble's the guy who did it. You have this red shifted light, these absorption lines, just like you do in any other galaxy, but they're in the wrong place. See how it is? The absorption lines for our sun, and this is the absorption lines. You don't have to write this tiny little things down, just the bigger one. Absorption lines for a supercluster of galaxies. See how it has the same lines, but they're shifted in the red direction. They're moved over. I'll try to get the direction right for your camera. Moved over that way, right? And so that means it's moving away from us. All right. So galaxies are moving away from us. Just like the train, you can tell if it's coming toward you or away from you by if the sound is Doppler shifted. Same thing with light. Now, nothing on Earth travels fast enough for us to be able to detect it this way. But the things, well, let me actually change that. The radar guns use Doppler shift for how they work. They change the frequency enough it can be detected. So this is, a real thing like the radar guns that used for speed guns. They use it for Doppler radar, which is how they do these kinds of maps. You probably heard of Doppler radar. What they're doing is detecting whether the raindrops are coming toward you or away from you. And so they can get a sense of the speed the raindrops are falling at, right? Well, what happens then, if you look at the light from galaxies, if it's moving toward you, let's say this is where the location of that spectral signature should be. But if you detect it blue shifted, and that means in the wrong way, shifted toward the blue, again, I gotta get my direction the same way yours is, then it's moving away from you. But if it's red shifted, excuse me, I said that wrong. If it's blue shifted, it's moving toward you. If it's red shifted, it's moving away from you. So Hubble came up with this way to measure the speed that the galaxies are moving away from us. Okay? And this is like some of his data, and you can see the spectral lines. This would be these bright lines here, if you can see them on your screen, are where they should be. And you can see that it's just a little bit off. And here, those two lines, just look for those two lines. You can see it's over here. It's shifted more toward the red, right? And here's the distance from it. And then here, even more toward the red, and more toward the red, and more toward the red. Okay, so the further away it is, the faster it's moving away from us. Okay? And so, here, again, another sort of graphic for that. Is like the stars nearby. This is where they are. The further away the galaxy, the more shifted it is toward the red. And what they realized then is as if they're moving the further away, the faster, what's happening is the galaxy is expanding. That's how they know that the galaxy is expanding. So I said that wrong, totally wrong. The universe is expanding. The universe of galaxies. Now, the galaxy is spiraling around. It's not actually expanding. I said that wrong. The universe of galaxies. When you look at the galaxies, they're moving further away from each other. And no matter where you are, it seems like you're in the center of the universe. Okay, we're going to try to draw this. Here's the thing. Okay, let's say that this is the spiral galaxy. This is us. All right? This is where we're located. We're in the Milky Way galaxy. And all of the stars that you see when you look up at the sky at night, those are stars. Or sometimes they might be planets if you're looking at Jupiter or Mars. You can't really see the galaxies with the naked eye unless you're in a really dark night and you have really good eyes. But with telescopes, they can detect them. Okay, so there's hundreds of billions actually stars in the Milky Way galaxy, about 300 billion stars in the Milky Way galaxy. And outside here, you have like the Andromeda galaxy. It's another spiral galaxy. And you have these other galaxies here, whatever their names are. There's a whole bunch of them, the Sombrero and So we're surrounded by galaxies. Okay, so go ahead and try to draw this if you can. I'm just trying to draw them where they're around there. And try not to lose track of which one's us. We don't have to draw too many because there's actually billions of them out there, right? And so, they get further and further away. Just to save time, I'm just going to go in one direction here. And here's the thing. This is the trick. When he started measuring the red shift of the galaxies, okay, the red shift of the light means it's shifted toward the red end of the spectrum, which means the wavelength is getting longer. Remember, with the Doppler shift of sound, when it's moving away from you, the pitch drops. So the longer the wavelength of sound, the lower the pitch, the faster it's moving away from you. And if it's moving away from you really fast, it'd be like, it would drop a lot. So you can tell how fast it's moving away by how much it's red shifted. And he realized, oh my gosh, all the galaxies are moving away from us. This is us. I think that's the one that I made us. But so the arrows there just showing the direction. Now, at first, when he started getting this data, wait, the galaxies are all moving away from us? That's bizarre. That means, what, are we the center of the universe? Do we have some sort of cosmic BO that everything's going to move away from us or something? And, I thought Galileo came up with the idea that we're not the center of the universe, that the sun is the center of the solar system and we're a planet that goes around it. Well, here's the thing. After getting more data, they realized it's not just everyone is moving away from us. Now, the length of the line is representing how fast it's moving away from us. Okay, I don't feel like drawing all the lines, but the further away from us it is, the faster it's moving away from us. Okay? Well, this one is out of place. But what that means then, to us, it looks like we're the center of the universe because everything's moving away from us. But what if you were at this other galaxy? Well, it would look like we're moving away from you, and this guy's moving away from him too. They would all be moving away from him too. So no matter where your perspective is, all the other galaxies are moving away from you. You see how that progressive bit of acceleration or the speed means this one's not only moving away from us, it's also moving away from that one because it's moving away faster. So what it is then, all the galaxies are moving away from each other. The universe is expanding. The further away you are, the faster it's going. That gives you a rate of expansion. Everywhere in the universe will seem like everybody's moving away from you, right? Okay, it's like, think of it as blowing up a balloon. What happens then, if you blow a balloon up, no single dot on that balloon would be the center, but all the dots are moving away from each other. And the further away it is, the more balloon stretchiness is between them, so the faster they're moving away from each other. Now this is Edwin Hubble got the data, and here what you have is the distance that the galaxies are away from us, and you can estimate that by the size of the galaxy under those fabulous telescopes. And here is how fast they're moving away from us. Okay? So, when you chart it as a graph, it gives you a line, and it gives you a rate of expansion for the universe. That means that the universe is expanding. All the things are moving away from each other. At least all the galaxies are. Now, if you ran that backwards, that means if you go back in time, everything would have been closer together. And if you go back further in time, it's even closer together. Back in time, further together, closer together, closer together, closer together, closer together, closer together. And you can figure out, well, at some point, everything would have been in the same spot. That would have been the Big Bang, where everything was all together. Now, it's not like you had all this stuff outside of the Big Bang where it showed up. It was like the entire universe showed up, and everything that's in the universe was in that single spot, okay? So about 12 to 15 billion years ago, usually it's 12.6 is what they say, but I'm going to go ahead and just give a little flexibility. Everything was at the same place. That is the idea of the Big Bang. That is why they believe the Big Bang happened, because when you look at the galaxies, you can tell they're moving away from us. And everything, it's not like we're in the center, because every one of them, no matter where you are, it would look like you're in the center. They're all moving away from each other. Okay? That means they all would have been together at the same spot. That is a mind-blowing idea. So again, you don't have to write down the the evidence says that about 12 to 15 billion years ago, the whole universe began. It exploded out from a single point, getting larger and larger as time went on, as expanding still. Sorry, this click the text here was in the way for the whoa, dude. Honestly, the proper and appropriate reaction to this is whoa, dude. You don't have to click that text. Sorry about that on the text. It's called the Big Bang. That's what today's lesson is all about. And now the Hubble Space Telescope was named after Edwin Hubble. And I'm going to tell you something that is like amazingly cool. Okay, I know that this lesson is getting on in time, but give me your attention again. Not only do they have the idea of, okay, the universe had a beginning about 12 billion years ago. How did it happen? I'm not even going to go into that at all, okay? But this is, I think, the coolest picture ever taken. All right? Here's what this is. It's called the Deep Field. They took the Hubble Space Telescope and they aimed it at a spot where nothing was. See, usually you say, okay, it's pretty expensive to aim the telescope and use it and get the data and stuff, So they were looking at, different things, planets and stars and galaxies, all these different things. And somebody had the idea, what if we look at the emptiest spot we can find in space? And that's what the Deep Field is. They looked at this spot that's the size of a dime viewed from 500 feet away. Tiny little point in space where there's no stars or nothing, right? And here's what they see. You know what these are? You see those, recognize those spiral shapes? Those are galaxies. So if you go back, and this, by the way, this picture, some of these galaxies are almost as old as the universe. We're looking back almost to the beginning of time. You don't think that's an amazing idea? And there's this other thing. I'm just going to show you this picture. What it is they think when everything was crammed together too tight, even light couldn't pass through it because it was so dense, nothing could pass through it. And there was a certain point where it became transparent, where there was enough space between the atoms that light could travel through them, right? And they estimated that light would be at a certain, wavelength or temperature. There's 3 degrees Kelvin is what it is. And it turns out, no matter which direction you look, you see the remnants of that leftover light from when the universe first became transparent. Okay, it's was discovered by accident. Actually, it's in the radio spectrum, which is the long waves, which you wouldn't be surprised about that because, if it's moving away from you, it would be redshifted, right? So it would be super long radio waves. Okay, so there you go. Big Bang.